Good day everyone, I'm Joshua Marta Pascual from BSE 3B Mathematics. So for today's video lesson, we're talking about Euler's Theorem in number theory. So let's start. Euler's Theorem, also known as Fermat-Euler's Theorem or Euler's Totient Theorem, states that if n and a are prime positive integers and p of n is Euler's Totient function, the a raised to the power of p of n is congruent to 1 modulo n. So let's define Euler's Totient function, which is generally denoted by p. It goes from the natural numbers to the natural numbers. Count the number of natural numbers between 1 and n that are relatively prime to n. So yun yung kakalabasan ng p of n. Then define the reduced residue system modulo n is a set of integers b1, b2, b3 up to bpn such that the GCD of br with n is 1. So every one of this number is relatively prime to n. And then if r is not equal to s, then br is not congruent to bs, modulo n. These are all incongruent modulo n and they are relatively prime to n. Here is the example to get an idea of p of n and some reduced residue systems. So here is the n equals 4. Then write all the numbers between 1 and 4 that are relatively prime to 4, so that will just give you the number 1 and 3. As you can see on the example, some reduced residue systems, the two numbers in this set, tell us that p of 4 is 2. Next is n equals 8. So to start, you should find the all numbers between 1 to 8 that are relatively prime to 8. So in this case, you get 1, 3, 5, 7. So that means p of 8 is 4. So the other sum residue or other sum reduced residue systems would be as follows. Here is the proof of Euler's theorem.
Lemma, we're ready to prove Eulers' theorem. The proof of this theorem should probably invoke reduced residue systems. So let's let B1, B2, all the way up to Bvn be a reduced residue system modulo n. And then our lemma implies that we have another reduced residue system modulo n, and that is given by a b1, a b2, all the way up to a b vn is also a reduced residue system. But let's recall what a reduced residue system is. It's a list of all possible residues modulo n that are relatively prime to n. So what does that tell us? That tells us that a b1 times a b2 all the way up to a b vn is congruent to b1, b2 all the way up to b vn, and that's occurring modulo n. And why is that? Well, that's because we're multiplying all possible residues modulo n just two different ways. One with our original reduced residue system, and one with our new reduced residue system built out of our original one and the number a. But let's notice that this is equal to a to the phi of n times x, where maybe we could say x is this product b1 up to b phi n. And then the right-hand side is just x mod n. And then finally, we can make the kind of obvious observation that the GCD of x with n is equal to 1. Well, that's because it's the product of a bunch of things that are relatively prime to n. But what does that mean? That means it has an inverse modulo n. We can multiply both sides by the inverse modulo n, and that leaves us with a to the phi of n is congruent to 1 mod n, which is exactly where we wanted this theorem to end. So now that we've got this taken care of, let's look at a quick corollary, which is famous in its own right as Fermat's little theorem. Okay, so as promised, we're going to look at a corollary, which is the famous Fermat's little theorem. So for this, we want to assume that we have a prime number called p and an integer a that is not a multiple of p. So in other words, p does not divide a. Then the conclusion is that a to the p minus 1 is congruent to 1 mod p. So why is this such a quick corollary? Well, that's because when you're dealing with primes, saying p does not divide a is equivalent to saying that the GCD of a with p is equal to 1. And then furthermore, phi of p is equal to p minus 1. Well, let's just think about that. You're counting up all of the numbers between 1 and p that are relatively prime to p. Well, that's clearly going to be everything except for p. So that's why we get p minus 1 there.
So here is the example. 5 to the 12 is congruent to modulo 6 or 36 modulo. Let's see what is congruent to modulo 36. So we start off by calculating 36. Then I'll use a formula which we discussed. So this is equal to 36 times 1 minus half times 1 times 1 minus third equals to the original number equals 12. So that we have here the 5 to the p of 36, and 5 and 36 are relatively prime. So this is 1. I hope you understand the lesson, and always keep safe. God bless. That's all.